So the last video cut off a little bit. So just to think again about the control of pH. So we need to make sure that the pH is kept the same each time for a fair test. And the way in which we keep the pH the same in practical experiments like this one is that we add what's called a pH buffer. So we're going to use a pH 7 buffer for this particular practical, and we might add the 2 centimeters cubed of pH 7 buffer every single time to make sure that the pH is maintained at pH 7 throughout. And again, what we would do when we did this experiment is at this stage here, we'd make sure that we measured out the volume of amylase. We might add the buffer at this particular point, measure out the starch suspension. Very often we might add the buffer here as well. Okay, make sure that they all come to the correct temperature and then mix them all together. But the pH buffer within here is going to make sure that the pH of this solution is maintained at pH 7. So what you need to next think about is what this might look like when you get to do it back at school. So I've posted this video in the classroom that you can watch. It's a bit slow, but you can speed it up. But this is the kind of protocol, and what you'll see here is that the lady that's demonstrating is going to take out samples, and she's going to use this iodine test as an indication of how quickly the reaction is taking place. Now, the other syllabus statement that you need to make sure that you're clear about is this one here. And this one is the same as the previous one, but instead of talking about temperature, we're talking about pH. So you also need to think about an experiment where you could control the pH as the independent variable, and then again measure the rate of reaction. So pH could be an independent variable in the same way that temperature could be an independent variable. This video is posted in the Google Classroom, so I want you to take a look at this and make sure that you're clear with your thinking. Now, the graphs that will be a result of this, we talked about the theory behind this already, but at very low temperature, we would expect a slow rate of reaction, but it's going to increase as the temperature increases, the kinetic energy is increasing. Then we're going to get to this part here. The rate of the reaction at this stage is highest. It's the optimum temperature. And for us, in our bodies, the optimum temperature for our enzymes is generally 37 degrees centigrade, which is the temperature of our body. But as soon as we go beyond 37 degrees, what's going to happen is that the enzyme denatures, and it denatures quickly. Okay, so you can see here that the curve is not symmetrical, right? It comes down very steeply at this point here. pH, as I said in the last video, the pH which is optimum is usually pH 7. Okay, and again, as we go lower, making it more acidic, or higher, making it more alkaline or basic, then we are again going to get the change in the shape of the enzyme and the denaturation of the enzyme. So the enzyme is denatured at very extremes of pH, both low and high. Now take care with this one, because the enzyme is going to be denatured at high temperatures, but at low temperature, the enzyme is said to be inactive, not denatured. Your task. First thing to do is just check through pages 6 and 8 and make sure that you have indeed tackled all of the questions which are within that booklet. I want you to watch the 2 videos, which are all about the prescribed practicals. And then I want you to do the questions on page 9 about this amylase practical and get as far as where it says, see the class pool data. Obviously, you can't go beyond that. If you haven't yet tried the past paper that I've posted for you to have a look at, then I'd also like you to do that. So in this lesson, I'd like you to make sure that we complete steps 1 through to steps 4. And if you don't get that done within the lesson, I would like you to do it as a homework exercise. As usual, I'll be in the Google Meet and ready to field questions when you have them.